Today we're going to do an application of ellipses. This is a very practical one. We're going to create equations, elliptical equations, for the orbits of the planets. And we're also going to create elliptical equations for the planetary shapes and then use those for some various scientific questions. First of all, make sure that you have with you the homework printed out, because what I'm going to do is just walk through parts of the homework and do this for a couple of the planets, and then I'll leave the rest up for you to do. So make sure you've got the data and the homework in front of you. Otherwise, you're not even know what I'm talking about. Okay. So I'm going to put up the data for 2 of the planets right here. Hopefully you can read that. If you can't, it's exactly the stuff on your worksheet, except you have it for 8 planets. Okay. I'm going to do this for Mercury and for Earth. So first of all, I'm going to go through what I have here. I have the semi-major axis, which in your equations was A. Remember, it's x squared over a squared. We have the eccentricity of the orbit, which I alluded to in the homework but didn't actually go through. So I'll go through that in a moment, the equation and how you get B, for example, from this. Then I have the radius of the Earth. We'll use that later. Radius of the planet around the equator. Then I also have the radius around the pole. And you'll see for some of the planets, these aren't even close to the same for some of them. For some of them, like Mercury right here, they are pretty close to each other. For the Earth, they are reasonably close, and some of the planets are not at all spherical. The radius of this we'll do in kilometers. I didn't mention this before. The semi-major axis we'll do in millions of kilometers. And then the length of the day, we'll use this in a moment as you'll see again. This is the length of the day relative to Earth. So Earth by definition is 1 day. This means that Mercury has a day length, basically dusk to dawn, or basically midnight to midnight. Mercury is 58.7 days, a much, much longer day than Earth. It's basically spinning much slower. And you'll find some of the planets are spinning faster than they are as you look through that, and some are spinning slower. Okay, so what we're going to first do is the whole goal of this is to come up with an equation for the orbits of these various planets around the sun. And we are going to assume that the center is 0, 0. Now, I'll talk in a moment. The center is not where the sun is, actually. The sun is at the foci. But we'll center the orbits around 0, 0. So the equations, therefore, are going to be x squared over a squared plus y squared over b squared equals 1. And again, we're going to assume that they're all horizontal axis. This is completely arbitrary, but we're going to assume the long direction is the x direction for the orbit, and the short direction is the y direction, and that'll be your b squared. Okay, so we'll start with we'll do a little table. I'm just going to do the first problem in your homework, which is for Mercury and for the Earth. We are going to find the semi-major axis, the semi-minor axis, which is b, and then finally the equation given that for the planet. Okay, orbiting the center and going around the sun. Okay, so let's start with, don't need this for the moment. We're going to start with the major axis, which is A, and B. A we are given, it's 57.91 million kilometers. So write that on your page. The minor axis you actually have to calculate from the eccentricity. The eccentricity E is given, the formula is given there, is 1 minus b squared over a squared. And I've got to solve this, given that I have E up here, and I have A, 57.91, I have to solve it for B. And I'm actually going to put this away just a second, put it to the side here, so that I can do this generally and then just use it. So I'm going to put E equals square root of 1 minus b squared over a squared. I'm going to solve that for B. So you may have done this in algebra, I'm not sure. This is actually how you solve radical equations. If you've got a radical, the first thing you do is you square both sides to get rid of the radical. Like that. Then what we're going to do is I want b squared, I want to solve for b, so I'm just going to multiply both sides by a squared. And what that does, and I'll talk about this when we do algebra next year, is it gets rid of all fractions, which generally you don't want to deal with fractions. This becomes a squared minus b squared, and this side becomes a squared times e squared. We're almost there. Now we just have to subtract a squared from both sides. And you get a squared e squared minus a squared equals negative b squared. Now I'm going to get rid of the negative sign. And I'm actually going to take the a squared out at the same time. So I'm going to multiply a squared. So a squared times, multiply both sides by negative 1. And you get b squared equals a squared plus, or minus a squared e squared. And then finally take the radical. And you get b is radical a squared minus a squared e squared. You could just take this a squared out as well to make it a little simpler. And just make it radical a, or a on the outside. And then the inside will just be 1 minus e squared. And there's my formula for b. Now, what that means in terms of what eccentricity is if b is a, b is exactly the same as a up here, this becomes 1, and the eccentricity becomes 0. So a perfect circle will have an eccentricity of 0. Any larger number, if you get up to, for example, where up here, if b is, for example, much, much smaller than a, this gets close to 0, and you just get an eccentricity of 1. So e goes between 0 and 1. And 0 would be essentially circular, and 1 would be essentially almost perfect. Well, you can't get exactly 1, but you get very, very elliptical, very, very squished. Use the very, very, use the very technical term, squished. Okay. So again, that's between 0 and 1. So for now, if I go back to my data, actually let me erase this. I need the formula. Equals this a squared 1 minus e squared. I'm just going to use this now, by the way. If you look at the data itself, you can see the Earth orbit around the Sun is pretty close to circular. Or around the center again, not the Sun. And Mercury is not so much. And I think, Mercury's probably, the most eccentric. If we had Pluto in here, you still do Pluto. Pluto has a much higher eccentricity. It's not at all circular, which is one of the reasons it was discarded as a planet. Okay, so let's do B now. So now all I have to do is plug in A is 57.91 and E is 0.2056. So I'll put those numbers in. And I'll just keep using that same formula over and again, so I'll use it when I get to Earth again as well. So 57.91 times radical of 1 minus 0.2056 squared. And do that, the radical of that. So I get 56.73 million kilometers. Again, it didn't make a huge difference. It still looks like it's somewhat circular, and it is, but you'll see in a moment when we do where the actual sun is, that it's quite off-center from the sun. Okay, there's my two numbers. And then finally, what do I want? The equation. So for the equation, I will get x squared over 57.91 squared. Just leave it like that. Totally fine. Again, this is million kilometers. Plus y squared over 56.73 squared equals 1. There we go. That's my equation of Mercury going around the center of the ellipse. Now we'll do the same thing for the Earth. The Earth has 149.60 million kilometers. And I just plug this formula in again, except now I have a very small eccentricity. So you're going to find this number is very close to 149.6 rather. Just make sure you put enough decimal points on it later, because we'll use those decimal points when we get to calculating something else. So don't round it to exactly that is my point. So anyway, you get 149.6 times 1 minus e squared. In this case, e is 0.0167 squared, and to the 0.5. 149.57 million kilometers. And my equation would be x squared over 149.6 squared, 60 squared, plus y squared over 149.57 squared equals 1. And there's the equation of the Earth's orbit around the Sun. Okay, so I want you to do those for the other planets. I might stop here and just do it for the other 7 or the other 6 planets in there. I don't think I took Pluto out of this. I did, yes. Okay, and then what I also want you to do is now graph these for 2 of them. You can pick any 2. But before we do that, I'm actually going to go through and calculate the foci for you to graph. So let's go through. So we got A and B. I need these numbers. So I'm going to take this and put it aside again. And we're going to use this to now calculate the foci. Remember the foci, focal length, let's do Mercury first. Okay, I'll put it down here. Let's do Mercury first. So Mercury, I'm going to leave this just for a second because I need the data. So c squared for ellipse is simply a squared minus b squared. So we can find c. I'm now doing problem 2, by the way. So a squared is 57.91 squared minus 56.73 squared, and then take the square root of that to get c. C is 11.63 million kilometers. Okay, so what does that mean? And I'll do this with a graph as well. So first of all, the equation itself looked pretty circular, but this is a pretty big number relative to 57.91. So what does that mean? What it means is that if I were to graph Mercury's equation, first of all, it's pretty close to circular, and this is not going to look the greatest, like my greatest circle. This is, what do you say, 57.91, and this from here to here, and this is 56.73. So certainly to the granular graph, those are going to look the same. However, c is 11.63, which is actually quite substantial here. It's right here and here. Distance between here and here is 11.63 million kilometers. That, right there, is actually where the sun is. It is not at the center. So Mercury goes very close to the sun here, and quite far away from the sun here. Now, which foci is the sun actually on? It's completely, it is actually on one physically, but remember that this is in space. You can just flip this over if you think you want to put it over here. It doesn't actually matter which one it is from a description of the ellipse perspective. However, here's the sun at 11.63. So what it means is the distance from the sun to the Mercury here, m, at some point is really short, and Mercury roasts. And sometimes it's pretty far. Those have terms. So first of all, let me give you the first line here on that second problem. Mercury, the foci 1 is 11.630. Foci 2 is negative 11.630. And then I have two terms in there, which are called the aphelion and the perihelion. The aphelion is the maximum distance from the sun. Helion means sun. So this is away from sun, and this is close to sun, is what that means. Aphelion is the furthest distance away from the sun. So you can get that from just taking this distance here, which is 57.91, and adding it to your focus, 11.63. So that number is 57.91 plus 11.63 is 69.54 million kilometers. That's the furthest is away. And then the closest is that 57.91 minus 11.63. Okay, and that's 46.28 million kilometers. So that's a huge difference, which, by the way, makes a massive difference in the temperature of the planet when you're here versus here. Okay, the last section wants you to graph that. I've already graphed that. That's section 3. And then there's one more question that asks, what is the implication for example, the temperature, which I talked about a bit, and therefore the ability to sustain life, what weather would look like, things like that. So again, stop there. Once you do the rest of the planets, you'll find that Mercury is the most extreme, by the way. At Earth, the difference is not very big because it's pretty close to a circular orbit. The focus is still slightly off center, but it's not as severe as this. All right, now we're going to do the same thing, except we're going to do it with the shape of the planets. So I'm going to erase this and put my data back up. And I will just do this for Earth. Mainly because if you look at the radius around the equator and the radius of the pole for Mercury, it is the same. In other words, it is essentially spherical. So what we're going to do is actually write an equation for the shape, the elliptical shape of the planet sliced through the equator first. So if you cut the Earth through the equator, what is that equation? And what is the equation if you slice through the poles? Now the slice through the equator, interestingly, it is simply just a circle. So the equation would be x squared over radius squared, 6378.1 squared, plus y squared, or 6378.1 squared, equals 1. In other words, it isn't elliptical, it's actually circular. You can multiply this by 63.78.1 and you get x squared plus y squared equals 6378.1 squared. X squared plus y squared is r squared. Again, we're going to go around 0, 0. Okay, so that's not very interesting. The more interesting is the equation around the poles. So if you cut the Earth, so you've got the Earth here, what it's saying basically is that this radius here, radius of the equator, is bigger than that radius, which is the radius to the pole. In other words, it's not actually a sphere, the Earth. And you'll see some of the other planets are really not spherical. Earth is still fairly spherical. This difference is not much. Okay, so let's do the equation of that. So to do that, you just do the radius. This is, if this is an ellipse, this is your minor axis, B, and this is your major axis, semi-major axis, A. So the equation is simply x squared over, and then we'll call this again, we'll call this the x part as well. So again, that's just arbitrary. So x squared over the radius of the equator, which is 6378.1 squared, plus y squared over 6356.1 squared equals 1. And that is actually, so this is the equation that should go in that for Earth, actually. Here's the equation. That goes in that table for Earth. And you can see then the equations are actually pretty easy for problem 1 in the second section because you're just using the numbers in the table. Now let's do eccentricity. I'm now going to use that equation I had before, which is E equals the square root of 1 minus B squared over A squared. Okay, so let's just put some numbers in. For the Earth, this is up here, 6356 is B, and this is A. Notice that B has to be smaller than A. It is by definition, but if it isn't, this number will be negative inside here. So you just do 1 minus B squared, which is 6356.8 squared divided by 6378.1 squared, and do that to the 0.5. Okay, the eccentricity of the Earth is, their shape is 0.081. So again, if it's 817, let's say. So if this number is close to 0, you have pretty much a circular Earth that direction, in other words, a sphere. If it's much larger, or sorry, if it's a much larger number, then basically the planet is squished down. You'll see, like for Mercury, for example, the eccentricity in that, since both of those are the same, will essentially be 0. It's not quite 0, actually, but to the accuracy of this, it's 0. Okay, so again, in the next section, I want you to do that for each of the planets. If you want to pause that there and do that, then go on to the second question, which asks, I just want you to think about this, which ones are more squished than others? So in other words, which ones have a higher eccentricity than others? And the question is, why? There's actually 2 reasons why, and you can get it from the information on the sheet itself and some general knowledge of the planets. So think about that and try to answer question 2. All right, that's just a walkthrough. I said I hope you'll be able to finish it from that. Thanks a lot. Until next time.